Hello, welcome back. And so today we're going to go ahead and continue with the discussion of stoichiometry. And so if you recall from the last session, we talked about the idea that in stoichiometry, what we're really doing is we're comparing the quantity of one particular substance in the chemical reaction to any other substance that participates in the same reaction. Okay? The way we can compare them, of course, is we could compare them by counting. So the easiest way to compare them is by number of moles of each, for example. And we find that with a balanced chemical reaction equation, then the coefficient in front of each of the substances allows us to do this mole-to-mole conversion where we have the mole ratios that allows us to really quickly figure out, if I have a certain number of moles of substance 1, then how many moles of substance 2 is going to be involved in a chemical reaction. That's the easiest way to do it. However, of course, things get a little bit more complex if we don't know the number of moles, but rather we're given the mass of a substance. Well, in that case, it's actually not that bad either. So you just have to remember that we can connect up mass with moles using the molar mass. So if we take the mass of substance 1, convert it to moles first, then we can compare moles of substance 1 to moles of substance 2 through the balance equation. Then from there, we can now figure out the mass of substance 2 afterwards, using the conversion back again. And so that's the general idea. Okay, so it sounds very simple, but of course the details gets a little bit complicated, so you have to make sure that you practice doing this with several examples to be good at it. Then of course there could be other kinds of difficulties that we can encounter while doing these sets of calculations. And one has to do with the fact that sometimes we might be given a substance that is not a pure substance, but rather we might have a mixture of some sort that has different components in it. And perhaps only one component within this mixture is going to participate in the reaction itself. So that means that we have things that are not going to be part of the reaction, but yet we have the information as to how much of it we have. So we have to somehow isolate the part from the whole and focus in on that part. So to do that, we need to use the concept called concentration. We want to be able to figure out the contribution that a particular part of a solution, of a particular mixture will have to the whole mixture itself. So let's take a look at what this looks like. So imagine if I want to look at this concept of concentration. What we're really looking at, of course, is the contribution of each part to the whole itself. So you imagine a very generic way of defining concentration might be that we're looking at, in general, the part of something divided by the whole of something. Okay? Now, of course, this is very general. We're going to be more specific in terms of putting this into actual use. So where do we see this? But it turns out we've already been doing something like this in the past when we talk about mass percent, mass percent composition of substances. So when we talk about the mass percent composition, what we're really doing is we're looking at the different contributions to the total mass of a particular compound, like water, for example. We know water is made up of two different elements, hydrogen and oxygen. So if I were to ask, if I have a particular sample of water, how much of it is being contributed to by the mass of hydrogen and how much is being contributed to by the mass of oxygen? And we have done calculations like that. And we found that for water, it is composed of about 11% hydrogen by mass and about 89% oxygen by mass. So this idea of mass percent concentration can actually be a definition of what we're looking at here. So we have the mass of the part divided by the mass of the whole. And of course, in this case, you have a fraction, so you multiply by 100% to give you a percent concentration. You could also keep track of concentration. Instead of using mass, you also use volume. So if it's more convenient to measure the volume of the part as well as the whole, then we have a volume percent calculation, where in this case, you take the volume of the part, divide by the volume of the whole, and again, multiply by 100%. The thing you have to keep in mind is that in both of those types of calculations, for both the mass percentage and the volume percentage, top and bottom, the part in the whole must be in the same unit. So the units has to cancel out in order for you to have a dimensionless percentage number. So keep that in mind. For us, however, in doing stoichiometry, we're probably more interested in looking at a slightly different kinds of concentration definition. In this case, we're going to define something called the molarity of a substance. A molarity comes in when we look at a situation where we might have a solution as our mixture. A solution, if you recall, is basically two or more substances that have the same physical form that are now mixed together into a mixture. And in this case, there's going to be one particular solution that we're really interested in. Of course, that is the aqueous solution. In an aqueous solution, what we have is we have a gas that is dissolved in water, or some sort of solid that is soluble and therefore is able to dissolve in water, and so on and so forth. So in this case, we now have really a mixture of two different things, water plus whatever you dissolve in it. And so in that case, we want to be able to keep track of the amount of whatever is dissolved in the water itself. In this case, because water is a liquid, it's much easier to now measure the volume of it. And in terms of the amount of the dissolved material, we're going to keep track of the amount based on the moles of substance that is dissolved in it. So by definition, molarity is going to be defined in the following way. We're going to go ahead and use the symbol capital M for molarity, and we're going to say that this is going to be equal to, in this case, the number of moles of the part that goes into the solution, and then divided by the volume of the whole solution. Volume of the whole solution. And we give the part and the whole specific names so that we can actually refer to them readily. So in terms of the part, we're going to call this the solute. So the solute is the part that goes into the solution in minor amounts. So those are the one that has a much smaller amount, and the gas that goes into the liquid water or the solid goes into there. That's the solute. And then, of course, the majority component, like the water, for example, is now going to be known as the solvent. And together, the solvent and the solute together will now be known as the solution. Now it's going to be the volume, of your solution. So of course, in this case, this is kind of very wordy, so we want to kind of summarize this a little bit. We can actually summarize this into a very simple relationship, where if I look at this definition of molarity, molarity is going to be defined now as the symbol we're going to use for number of moles is going to be the lowercase n. So this is the number of moles of your solute. So this is now the number of moles. And then, of course, the volume of your solution. Volume of solution. So if you remember, n, is now the number of moles of something. V, of course, is now volume. Volume measure. The number of moles is pretty standard. We know that number of moles is measured in units of moles, obviously. Volume, to standardize it, volume we want to go ahead and standardize it in terms of a liter as our standard volume. And so in that case, we can now go ahead and define a brand new unit. Now in this case, notice that in this case, this is now used as a symbol that represents the physical quantity. So this capital M is the molarity by definition, kind of like density, for example. Then this is defined as number of moles over the volume. But we can also use that capital M as a unit, so to speak, so we can put it after a number so that it has a certain meaning. So by definition, when we use this M, this is now going to be defined in terms of the number of moles of something divided by 1 liter. So when we see the combination of moles per liter, then I can now substitute it with this M for molarity measurement. So now it tells us, we're talking about the amount of a particular part in a certain volume of the whole solution itself. And so let's take a look at how we can actually use this now in our calculation and determining the molarity of certain kinds of substances. So let's take a look at an example. Let's say I'm going to go ahead and take a solid material and I'm going to dissolve it in water. And so let's go ahead and dissolve. In this case, let's say we have 37.895 grams of a certain compound, let's say cobalt 2 chloride. So this is going to be solid to begin with in water. So we're going to put it in a little bit of water, mix it up a little bit, and let's start to dissolve. And then once we have most dissolved, we're going to add additional water in there until we have a certain volume. So then we go ahead and dilute it, to a total volume of, let's say 250.0 milliliters. So we have now just created a solution, a mixture of a solid dissolved in a liquid solution. And so the question then is, what is the molarity of this particular solution? So to do this, remember, we have to first of all, be able to figure out the fact that I need to have a certain number of moles of my material. So here I'm given grams. I don't know what the mole number is. So I need to, of course, do a conversion to begin with. So also I need to know, what the volume of the solution is. Well, that's not bad because I'm given the volume right over here. So that looks pretty good. So the idea is that I need to know the quantity of my solute and then the volume of my solution. So this is going to start like this. A lot of it has to do with, again, unit conversion, so that you're going to end up with a proper unit. The key is to get the molarity. You want to end up with the units of moles per liter as your standard units of measurement. So let's start off with then 37.895 grams of COCO2, and of course divided by, so this is again, amount of solute over volume. The volume is 250.0 milliliters. Okay? The first thing I need to do, of course, is to make sure that I convert my grams to moles of substance. And we know how to do that. So grams of COCO2 to moles of COCO2 for every 1 mole. And if you go ahead and look it up, you find that the molar mass is roughly 129.8386 grams. So notice that grams now goes away. That looks pretty good. The next step, of course, okay, although I have moles on the top, I don't have the proper unit on the bottom for volume. So I need to go ahead and convert that. So I know that, for example, 1,000 milliliters is the same as 1 liter. So now that goes away. Now I have the proper unit of moles per liter. So now I'm ready to do the calculation. So when I work out the numerical value, then I find that I end up with a number like 1.167, okay? And in this case, this is going to be now moles per liter of COCO2. And as I said before, once we have this combination of units of moles per liter, I can now replace that with the symbol for molarity, okay? And so I have this as my final answer. So what I produce is when I dissolve this much cobalt 2 chloride into water to make a 250.0 milliliter sample of a solution, I end up with a solution that is now 1.167 molar solution of a cobalt 2 chloride. Okay, so that's how you kind of refer to this. But this again relates the number of moles of something to the volume of a solution to its molarity. Okay, it's very similar to like density is equal to mass over volume, except this time is moles over volume, and this is called molarity instead of density. Okay, so same kind of idea mathematically. But sometimes it turns out you can also do other things. Within a particular solution, you might actually have different components in there, and you can talk about the molarity of the various components and see what happens. Basically, think of this as kind of like concentration of your dissolved material in the overall whole solution itself. So let's imagine I have a slightly different situation now. Let's do another example. Let's say that I have a 0.100 mole. Let's see, mole. So I have moles of CaNO3. So this is calcium nitrate. Okay, and let's say I have this dissolved in a solution so that I have a total of 100.0 milliliter of solution. So here I have this much calcium nitrate dissolved to make this solution right over there. So the question might be, okay, what is now the molarity of various things? What is the molarity of the calcium nitrate? Okay, what is the molarity of, what about if I'm only interested in the calcium ion in there? Okay, so the idea is that when you put this thing into water, well, nitrate is always soluble. So once you put it in water, it's going to break apart. So it's going to basically separate into its basic ionic components. So I can actually think about, well, what if I only am interested in the calcium? What would be the molarity for that? And finally, of course, what is the molarity for, let's say, NO3 minus? So again, I could have a polyatomic ion floating in there. I can ask, well, what is the concentration of that inside of my solution? I can go about finding each of these three things. So how do I go about doing that? Well, we go back to, again, our definition of molarity. So in this case, I can have now molarity of calcium nitrate equals to, by definition, the number of moles of your solute, or here's the number of moles of your solute, 0.100 moles of calcium nitrate divided by the volume. Okay, the volume then, of course, in this case, that's going to be 100.0 milliliters. Okay, of course, in this case, I don't have the right unit, so I need to go ahead and do a conversion. Make sure I convert from milliliters to liters. That goes away. So 0.1 times 1,000 divided by 100. Well, guess what? You end up with a very nice number, 1.00. In this case, you have moles per liter now. So I can put the capital M over there of now CaNO3 2. Okay? So I have a 1 molar solution of calcium nitrate. That seems pretty easy. What about the next part now? What about if I want to find now, just the calcium ions? Just the calcium ions. Then what happens? Okay? Well, in this case, I know what the solution is. I have this solution in there, so I know I have 1.00 moles of CaNO3 2 per 1 liter, of my solution. Then I ask, well, of this 1 mole of CaNO3, how many moles of calcium ion do I have? Well, then I can now do a conversion right over here. So now I can look at moles of Ca plus 2 ion to moles of CaNO3 2. Okay? Well, let's take a look. Every time you have this broken up, you're going to have 1 calcium ion coming off, okay, for every compound unit formula you have there. So this is going to be a 1-to-1 ratio. So when you work that out, okay, that goes away. You now have 1 mole of, okay, I should say, this is the other way around. So the calcium ion should be on the top, okay, and then calcium nitrate should be on the bottom. There you go. Okay, so that goes away, and now you just have 1 mole per liter. So that's going to be again your 1.00 molar. In this case, just calcium ions. So in this solution, you have a 1 molar solution of calcium ion as well. The next step, of course, is to find this last one over here. So now if you look at for NO3 minus, you do the exact same thing, 1.00 moles of CaNO3 2 over 1 liter by definition. This is what we mean by 1 molar. Then we can now go ahead and do the conversion. Again, for every 1 mole of CaNO3 2, how many moles of NO3 minus do I have? Well, notice in this case, I now have a parenthesis with a 2 here. Because each of these has only a -1 charge, I need 2 of them to balance out my calcium plus 2 charge. So that means when this is taken apart, it now has 2 separate nitric ion floating around. So that's going to be a 2 up front there. So when you work this out, you end up with a 2.00 molar concentration of NO3 minus. Okay? So depending on which of these 2 are going to be, let's say, your reactant in a chemical reaction, you can then be able to figure out how much product you might end up with at this point. So okay, you can actually look at the molar concentration for different substances within the solution itself, depending on what you're interested in. Sometimes you're interested in the whole substance. Sometimes you might be only interested in the ions themselves. Okay? For our part, most of the time we're just going to be focusing on that particular substance because that's what we're going to be using for our balanced chemical reaction equation. But just saying that you can actually separate them out like this as well. But the key is nothing new. It is still the idea of finding the part over the whole in some sort of measurable, in this case, moles per liter volume. Okay? All right, so that part is the molar concentration. And what it does is it allows you now to keep track of the amount of substance in a slightly different way. So sometimes instead of giving you the mass of a solid material, I might now give you the volume of a particular solution. And based on that, you can then be able to figure out the number of moles of that substance, and then you can go ahead and use the mole ratios to find the amount of another substance in the reaction itself. All right, so in general, when you look at stoichiometric calculations, we're making some very important assumptions as well. We're assuming that when we have a reaction and we have those proper ratios, the coefficients of a balanced equation, that when the reaction takes place, that all the reactants gets used up in the reaction and all of it goes into producing products. That's the ideal situation. Of course, in reality, that's not always going to be the case. In reality, of course, there's going to be a situation where you may actually have all the ingredients that you need, all the reactants that you need, but they don't necessarily have to be in the proper stoichiometric ratios. So when you combine them together to form products to undergo a chemical reaction, you may actually have a certain number of reactants left over from your reaction. Okay? So that means you're going to run out of a particular reactant, but you may have leftovers of others. And so how do we keep track of something like that? What happens when we run out of a particular reactant in a chemical reaction? So let's take a look at now something called limiting reactant. And so the idea is that if your reactants are not in the proper stoichiometric ratios, or like the coefficients in front of the balance equation, then as you allow them to react, there's going to be one that will always run out first. Okay, usually. You could have actually 2 that run out simultaneously, but the idea is that you're going to run out of something. And that something you run out of would then, limit the amount of product you can make. Because once that is gone, you can't continue to undergo the chemical reaction because you don't have anything now to combine with whatever you don't have. So you can't continue making products. So the production of products basically ceases. So the reactant that runs out basically limits the amount of a product you can make. We call that the limiting reactant. So let's see what that looks like. So this idea of limiting reactant. And usually we are just going to use LR for short to kind of represent the limiting reactants when we talk about it, when we do a discussion. Now, a lot of times, of course, we could go ahead and go through a specific example right away and see, but sometimes it's easier we have an analogy to kind of see what it actually means. Okay, so let's take a look at the analogy of making sandwiches, for example. We all make sandwiches, right? So we can kind of see how this actually comes into play when we make sandwiches. So let's say, how do we go about making sandwiches? What goes into making sandwiches? Well, let's say we're going to make some ham sandwiches. So under ham sandwiches, let's go ahead and erase this and put the equation, so to speak, for making sandwiches up here. So we're going to go ahead and start off with 2 slices of bread. 2 slices of bread. I'll combine this then with 1 slice of cheese. And I'm going to go ahead and put in, of course, I need my vegetables as well, so I'm going to go ahead and 2 pieces of lettuce. And of course, I need my ham. So I'm going to have 3 pieces or 3 slices of ham in my sandwich. And finally, when I put it all together, that will then give me 1 sandwich. So this is now my balanced chemical reaction equation, so to speak, for making ham sandwiches. So these are the coefficients, the relative amounts. Now, of course, what if then I have a certain amount of ingredients to start off with? So I look in my refrigerator, and I find that I have the following in my refrigerator. I find that I have 16 slices of bread. And let's see, 7 slices of cheese. 14 pieces of lettuce. And let's say, I think 18 slices of ham. So these are all leftovers from the last time I made ham sandwich, and this is what I have in my fridge. So the question then is this: having these ingredients, how many sandwiches can I make? How many sandwiches can I make? Well, you say, well, I mean, let's take a look, right? The key here is, of course, as I begin making the sandwiches in these combinations, eventually I'm going to run out of something. So what is it that I'm going to run out of? And that's something, of course, is going to be my limiting reactant. And so the one way you can actually do this is you can ask yourself, if I'm given a whole bunch of different ingredients here, you can ask, well, how many sandwiches can I make with each of these ingredients, if that's the only thing I'm going to be using? So how do you figure that out? Well, you're just going to do a stoichiometric calculation based on the ratios that you see in your balance equation. So I can say, well, let's take a look at my bread. If I were able to use all 16 slices of bread, how many sandwiches could I conceivably make? I can just then do a very simple conversion where I now have slices of, I'm just going to go ahead and abbreviate it, slices of bread down here, and then of course, sandwiches up here. So I find that for every 2 slices of bread, I can make 1 sandwich over there. So if I work this out, I find that, I should be able to make 8 sandwiches based on the 16 slices of bread that I have. So I say, that's not bad. I can make 8 sandwiches. But, I also have other ingredients. So what about the other ingredient? Well, let's take a look at the slices of cheese. So for slices of cheese in making sandwiches, I find that I need 1 slice of cheese for every 1 sandwich. This is now a 1-to-1 ratio. So when I cross that out, I find that I have 7 times, I can make only 7 sandwiches with my 7 slices of cheese. So obviously, this was a little bit too optimistic. I won't be able to make 8. I can make 7 at this point based on using up all my cheeses. But then, of course, that's not the end. I can now go ahead and do the same thing for pieces of lettuce, making sandwiches. And I notice that for pieces of lettuce, I need 2 pieces of lettuce for 1 sandwich. So now 14, blah, blah. I end up with, so with the amount of lettuce I have, I can also make 7 sandwiches. That's looking pretty good. Maybe 7 sandwiches. Let's go to the last one. So now when I do the last one, this is now pieces of ham in making sandwiches. Here, for every 1 sandwich, I need 3 slices of ham. So when I work this one out, however, I end up with 6 sandwiches. So in this case, this limits the number of sandwiches that I can actually conceivably make. I can only make 6 sandwiches based on my 18 pieces of ham. Although I have enough bread to make 8, I can't use up all the bread. So this gets used up completely at the end. This is now going to be your limiting reactant, basically. And it then dictates how many sandwiches you actually make. You actually make 6 sandwiches, so then this will then be 6 sandwiches as your end product here. You cannot make 7, you cannot make 8, because once you run out of ham, okay, you may be able to make other kinds of sandwiches, but you're not going to make any more ham sandwiches. You lose the ham sandwiches. Okay? And so it's very important that once you identify the limiting reactant, that you do every calculation in regards to finding out what the other things are, okay, based on that limiting reactant, especially in terms of product production. So that will limit the amount of product you can actually make. So in this case, we actually did calculations for each of your reactants to figure out how much they will produce, and then from there determine which one is limiting. There are other ways you could do it, especially if you have fewer ingredients, so to speak, fewer reactants. And if you have only 2 reactants, you could actually take one and then try to figure out how much you need of the other. So we can kind of take a look at an example of those. So to further discuss this, let's go ahead and take a look at a couple other examples to see how this works in terms of limiting reactants. So let's do a real simple one. We have a couple of simple ones. We have seen this before. What if I want to go ahead and make water using oxygen and hydrogen? So from visual, I have here, okay, some oxygen and some hydrogen. So if each of these, let's say, represent a particular value, let's say 1 mole of that substance, I here have 1, 2, 3 moles of oxygen, 1, 2, 3, 4, 5, 6, 7, 8, 9 moles of hydrogen. And what I want to do, of course, is I want to go ahead and make water on the other side like this. The question is, okay, how much water can I make on this side based on what I have right over here? So given that I have 3 moles of oxygen and 9 moles of hydrogen, how many moles of water can I make? So let's see what that looks like. The first thing you need to do is, again, you need to write down a balanced equation. It's always the starting point. I have now H2 plus O2 giving me H2O. And so you find that you have to put a 2 here, and 1 here. Okay? So there's your balanced equation. And then, of course, you're given the following. So put down given. Okay? In this case, you have 3 moles of O2 and 9 moles of H2. So the first thing you're going to do is, before you actually figure out how much water you're going to make, is ask yourself, which one is your limiting reactant? Okay? So of these 2, which one is your limiting reactant? So how do you go about doing that? Well, one of the ways you can do it is you could, again, calculate the amount of product you could get for each one of these, and then look for the smaller one. Another way to do it is actually compare the 2 of them and see if I have a certain amount of the one, and I want to use it all up, how much of the others do I need? So for example, if I look at this part right here, I'm given 3 moles of oxygen. I'm going to ask, well, if I want to use up all 3 moles of my oxygen, how much hydrogen would I need? Well, let's take a look. I can do a conversion real easily just by using the mole ratios. So moles of O2 to moles of H2, that will go away. In this case, H2 should have a 2 in front, O2 should have a 1 in front. So that means I have now 6 moles of H2 needed. So I need 6 moles of H2 in order for me to use up all 3 moles of my oxygen. The question is, do I have enough? Well, let's take a look. I need 6. Oh, I have 9. Sure enough, I have more than enough. So here's the thing. If I have more than enough, that means that I'm not going to be able to use it all up. There's going to be leftovers of this substance. If I have leftovers, that means I've used up all of the other. So this tells me right away, okay, O2 is now my limiting reactant. That's my limiting reactant. Now what if I start off with the hydrogen? Would that give me the same conclusion? Well, let's see. As it turns out, you don't have to do both, you just have to do one. But it's always good to check just to make sure we get the same answer. So if I start off with now, let's say 9 moles, okay, of H2, and I ask, if I want to use up all my hydrogen, how much oxygen would I need? Well, now the mole ratio is going to be, okay, moles of O2 over moles of H2. And so in this case, 1 on top, 2 on the bottom. Okay? So that goes away. 9 times the other, oh, this gives me 4.5 moles of O2 needed. So I look at, this is what I need. This is what I have. I only have 3 moles. So I don't have enough. If you don't have enough, that means this is not going to be used up way before the other one. And again, same conclusion. This is your limiting reactant. Okay? So once you have that, then I can now calculate the amount of water that I'll produce. I have to base it off of my limiting reactant. So this tells me, okay, that means I now got to go to my limiting reactant, which is now 3 moles, okay, of O2. I go ahead and do the conversion. So from moles of O2 to moles of H2O. In this case, there's a 2 in front of here, there's a 1 in front of there. That goes away, that gives me 6 moles of water will be produced from this reaction. Okay? So what happens in this case then, of course, is now you have 1, 2, 3, 4, 5, 6 moles of water being produced, but here's the catch. In this case, all of this gets used up, okay? But you only need to use up only what? 6 moles of hydrogen. So 3 of these are not going to be used up. So while these goes into the actual reaction itself, you now have this as your leftover. Okay, leftover. So this is now your balance equation here. These are leftovers from your excess that you have. But this now, things that get completely used up, this is now your limiting reactant, your oxygen. Okay? Now sometimes it gets a little tricky because sometimes we like to take shortcuts and we forget about certain things. So some people say, well, let's start this way. I know I have 3 here, I have 9 here, I have a lot less here, so maybe this is going to be my limiting reactant because I have so few of it. And in some cases, that's the case, just like in this case here. But it's not always going to be so. So that's going to show you why that is the case. Let's go ahead and replace the oxygen now with a nitrogen. So let's say I have nitrogen here now, and I have oxygen here, hydrogen here. Let's see what happens when I go ahead and make this substance over here now. I'm going to make ammonia using the nitrogen and oxygen, hydrogen. Let's see what happens in this case. Well, in this case, I have a different chemical reaction equation, and I need to balance that. Always remember, you start off with the balanced chemical reaction equation. In this case, I'm now going to be using H2, that's N2, giving me NH3. So now when I look at the coefficients in front, I have an odd number here, even number here, so I'm going to put an even number in front here. 2 times 2 gives me 6, that means I put a 3 out front here, and then 1 times 2, 2 times 1, they balance. So now this is my balance equation. Okay? Once I have that, of course, is now I'm given, okay, in this case, 4 moles of N2, and then I still have my 9 moles of H2. So the question is, in this case, is which one is now going to be my limiting reactant? Okay? So you do the same thing as we did before. We go ahead and pick one, doesn't matter which one. Let's say nitrogen. You say 4 moles of N2, but I go ahead and calculate the number of moles of hydrogen I need, then I do my mole ratio comparison. Moles of hydrogen over here. And so from my coefficient, I see that, okay, for 3 moles of H2, I will basically react with every 1 mole of N2. So now that goes away. That tells you you need 12 moles of H2. You need it. Well, let's take a look. I need 12 moles. I only have 9 moles. That means that before I can use up all my nitrogen, I've already got done with my hydrogen. So that means that, wait, I don't have enough. That means that this then must be my limiting reactant. Okay? Limiting reactant. And again, either way, you can still confirm that if I had to start off with 9 moles of H2 to begin with, okay, if I do the calculation this way, I have H2 over here, moles of N2 over here. In this case, again, the 3 now goes on the bottom, 1 goes on top. This tells me I need 3 moles of N2. And sure enough, I need 3 moles. I have 4 moles. I have more than enough. Again, I'm going to run out of hydrogen from so. Either one you calculate, you still get the same result that this is now your limiting reactant. Okay? Limiting reactant. So that means if to calculate the product, I now have my 9 moles, okay, of H2, okay, converting moles of H2 to moles of NH3. Now I have 2 moles up there, I have 3 moles down here. 9 divided by 3 gives me, okay, 3 times 2 gives me 6 moles of NH3 produced. Okay? So that means on the other side, I can expect to see now 6 of these on this side as well. Okay? But notice the difference in this case. Okay? In this case, it is the quantity that you had seemingly more of that gets used up. And so now this is going to be all the things that will react to produce your 6th product there. And now you have an extra nitrogen that's not used up. So this is now your excess. Okay? So in this case, the thing that you have fewer of actually gets left behind, okay, in excess. So don't just say, okay, whatever I have less of, I'm going to go ahead and use that. You can't use it in terms of the lesser mass or the lesser number of moles. Either one of those you don't know until you look at the coefficients in your balance equation. So keep that in mind. All right. So in this case, what we find is that, okay, this is really nice. Okay, it allows us to, again, look at the situation where I can have a certain expectation in terms of 3 moles of hydrogen will combine with 1 mole of nitrogen to form a 2 moles of ammonia and so on and so forth. But keep in mind that this is, again, an ideal situation. In reality, as it turns out, it may not necessarily be the case. So the number that we get over here, the 6 moles of NH3, we call this the theoretical yield. This is what we predict based on our understanding of chemical reaction equations like this, okay? And doing stoichiometry, this is what we predict that we should end up with. But in reality, as it turns out, as the reaction actually undergo its progress, what can happen is that the product that you produce may actually get in the way of the reactants or whatever remaining of the reactant to come together and try to react. So some of them may actually be kept so far apart they don't have a chance to react with each other. And that makes it very difficult for you to produce additional products. And so sometimes when you actually collect all the products that you have made in a chemical reaction that have seemingly come to an end, you find that you don't quite get what you expect. What you actually get at the end is what we call the actual yield. So the difference between theoretical yield and actual yield. So the theoretical yield is what is being predicted. This is the predicted yield from the balanced chemical reaction equation and stoichiometry. Whereas actual yield is what you actually collect at the end of the reaction. So a lot of time, of course, we want to do this for real. We want this to be commercially productive. So we want to produce a certain amount of product that we can then sell or use for some purpose. So this is going to be very important. And so if you can imagine now, let's say we call theoretical yield as Ty, actual yield as Ay, we can now compare what we actually get to what we predict and look at something called the efficiency, so to speak. We usually call this the percent yield. The percent yield tells us how much the actual yield actually deviates from my theoretical expectations. So for example, this is now going to be calculated using the actual yield divided by the theoretical yield times 100%. So if I expect to find, let's say, 6 moles of NH3 and only end up with, let's say, 3 moles of NH3, then if I take the 3 moles divided by the 6 moles, that gives me 0.5 times 100%, that gives me a 50% yield. In other words, I want to get 50% of what I predicted I would get. And apparently that's not going to be very efficient. So why do we even need to figure out the percent yield? Because sometimes, as it turns out, there may be more than one way of producing a certain product. Let's say for making ammonia, for example. So the idea is that if you're going to commercially produce ammonia, you want to pick the reaction that will give you the best percent yield so that you don't waste your reactant. You don't get things that are not reacted and therefore gets thrown out with the trash, so to speak. You want to make sure to use up as much of your reactant and produce a product that you want, maximize your product production as much as possible. And that's the idea. Also, sometimes the reason for having, let's say, limiting reactant might be for a similar situation where you want to maximize the production of the product. So let's say if you have 2 ingredients or 2 reactants that goes into a reaction. One is a very, very expensive reactant, and the other is really, really cheap. So the idea is that when you allow them to interact, you really want to use up all of the expensive reactants to produce product because that's what you want at the end. So to guarantee that, you put in a lot more. You put in a lot more of the cheaper material. So you put in the cheaper material in excess. So that means you have a lot of opportunity for that cheap material to grab hold of that expensive material and convert it and change it into the product that you want. And so that might be one of the reasons why you might actually have limiting reactants in the first place. And of course, there's going to be other examples, other reasons for that. Let's discuss in the textbook as well. So you can kind of read up on that. But the idea is that this really allows us now to look at the efficiency of a particular chemical reaction. The higher the percent yield is, the better it is in converting reactants to products. And so for commercial production, that could be very important. All right, so having talked about all of this, let's go and take a look at a particular example that kind of wraps up everything that we talked about today into a nice little package. So let's talk about making hydrogen gas. As we said in the past, hydrogen is actually a very interesting material in that it is very reactive, very, very volatile, but also because of its very low mass, its very low weight, it doesn't hang around in our atmosphere very much. It has such low mass that its kinetic motion allows it to actually escape into space very, very easily. The Earth's gravitational pull is not strong enough to hold it near the surface of the Earth. Whereas things like nitrogen and oxygen, they're heavy or massive enough that the gravitational pull will actually keep it here on Earth. So where do we get hydrogen gas then if we need it for some sort of experiment, for example? Well, what we have to do is liberate it. We have to now make it, so to speak, and separate it from compounds within which it is found. So part of it, of course, is you can actually separate it from water, for example, using electricity. So if I were to run electricity with water, I can actually separate it into hydrogen and oxygen. But then that's not the most convenient way of producing hydrogen. Another very convenient way is actually looking at the situation where you might also find hydrogen. Of course, it's going to be in acids. So anytime you have a strong acid, for example, you have a lot of hydrogen ion, somehow you're able to take that hydrogen ion, okay, and basically, okay, reduce it, allow it, an electron to jump onto it. You can then make it into an elemental hydrogen. It would then be able to combine with another hydrogen and float off as H2 gas. And so one very simple way of creating hydrogen gas would be, okay, an acid reacting with a metal that is reactive. So for example, okay, if I have zinc and I basically drop it into hydrochloric acid, okay, I would then be able to produce, okay, my products. In this case, this is going to be zinc 2 chloride, okay. This is now going to be aqueous, plus there is my magical, okay, hydrogen gas. So in this case, let's go ahead and balance the equation so that we can see where we start. So it looks like over here I have 1 hydrogen, 2 there, so put a 1 here, put a 2 here. That'll be 2 chloride, that looks good. It's 1 here, 1 here. You have now your balance equation. Okay? So now I have this balance equation. This allows me to now produce hydrogen gas. So let's assume that you're given a certain amount. Okay? So let's say that you're given, in this case, let's say 250 grams of zinc. In this case, I'm going to go ahead and put a decimal point to remind you that this is actually 3 sig figs. Okay? And let's say that you have a certain amount of hydrochloric acid, but now in this case, you're probably going to be measuring the volume of your hydrochloric acid, okay? And of course, in this case, the hydrochloric acid is going to have a certain concentration of HCl in there, hydrogen chloride in there. So this is hydrogen chloride gas that's been dissolved in, okay, water as a solvent, okay? So that's your hydrochloric solution. So in this case, let's say you have 800, again, I'm putting a decimal point to remind me this is now 3 sig figs, okay? Let's say milliliters, okay? In this case, let's say we have a 6.00 molar HCl solution. So this is called a 6 molar concentrated hydrochloric acid. This is a pretty concentrated acid, so this would be very dangerous. If you're not careful, you pour it on yourself, it will burn severely, okay? And so let's say that we want to now find the following. So given this, let's go ahead and find 2 things. So the first thing I'm going to find is, I'm going to find, let's say, 1, the mass of H2 gas produced. Okay, so how much hydrogen gas were we able to make from this particular process? And secondly, let's say that we want to go ahead and find the percent yield, okay, if, okay, 4.50 grams of H2 gas it was collected, okay, at the end of your, okay, reaction. So let's find these 2 things. All right, so how do I go about doing this? Well, in this case, I want to now compare, okay, my reactants over here and be able to somehow connect up the reactant with my product over here. A way that I can do that is I can compare them by moles if I know the mole ratios up here. The problem is I don't have this in moles yet. I need to somehow convert them to moles. So the first step, of course, is to convert the mass of your reactants into moles of something. So I need to go ahead and use that as my first step. So let's take a look at the first step over here, okay? So let's take a look at the first situation. So let's take a look at the zinc. So for the zinc, I'm going to go ahead and convert 250.0 grams of zinc into moles. So the very first thing that you do in most cases is somehow convert a measurable quantity like mass or volume of some sort into moles. You always want to get moles before you start comparing things on your reaction equation. So in this case, you have this. You have grams of zinc to moles of zinc. For every 1 mole, if you look up the molar mass for zinc, you find it's going to be 65.39 grams. And if you work that out, you end up with, you can notice I have 3 sig figs here, but I know that I'm going to be using this to do other calculations later on. So I'm going to carry 1 extra sig fig just so that I can, okay, avoid the round off errors too soon. So let's say this is around 3.823 moles of zinc is what I start off with. So now I have moles of zinc. That's a pretty good step. Okay? So this guy I'm thinking again, okay, the quantity of substance 1, mass of substance 1, and convert it to moles of substance 1. That's the first step. Okay? The problem is I can't just use this to figure out my hydrogen because I don't know if I'm going to be able to use up all my zinc. because I have two quantities here. I don't know which one is the limiting reactant yet, so I need to kind of figure that out first. So in this case, let's take a look at the HCl now. So once I have that, I'll compare it to the amount of HCl that I have. So how do I get that into moles of HCl? Well, somehow I have volume to begin with, so somehow I convert volumes, to moles, volume to moles. How do I do that? Well, if you recall from before, the molarity is equal to the number of moles of your solute divided by your volume of your solution. So if I want to find the number of moles, I can now rearrange this. Then the number of moles of solute must then be equal to the molarity multiplied by the volume of your solution. Okay? So this is a matter of just rearranging this. So this is what I'm looking for, number of moles. And where's my molarity? Well, here's my molarity, 6.00. Remember, this is moles per liter. That's the definition of this symbol over here. And then, of course, I have my volume, 800 milliliters. So that looks pretty good. So let's start off with now my 800, let's go and start off this way. In this case, let's start off by looking at the fact that N of my solute, in this case, this is going to be HCl. Okay, so the number of moles of HCl is going to be equal to, I have my molarity, which is 6.00. Now I'm going to go ahead and convert this capital M back into my moles per liter unit, of HCl. Then I'll multiply it now by the volume, which is 800 milliliters. The problem, of course, is that the liter milliliters don't quite cancel, so I need to do one more conversion. Okay, so I have then 1,000 milliliter to 1 liter. So now notice that, oh, look at that, that's kind of nice. Milliliter goes away, the liter goes away. So now I have 6 times 8 times divided by 1,000. So when you work all that out, you end up with, basically 4.800 moles of HCl. Okay? So again, I keep one extra decimal place, just so that I have one more sig fix to work with. Okay? So the question is, I now have these two substances, which one is now my limiting reactant? Well, to find the limiting reactant, I can ask a question. I can ask, well, if I start off with, let's say, this thing over here, then how many moles of HCl would I need? Well, let's take a look. So if I have 3.823 moles of zinc, then I would need, so moles of zinc here, moles of HCl over here. I find that, okay, in this case, I have a 2 HCl in front of HCl, and then 1 in front of my zinc. That goes away, okay? And that'll give me a value of, 7.646 moles of HCl needed. Okay? So that's how much I need. Well, how much do I have? I have this much. So I compare now this to what I have. Well, guess what? I don't have enough. What does that mean? If I don't have enough, that means that this gets used up first. This is now my limiting reactant. So the HCl is now my limiting reactant. That would then limit the amount of hydrogen gas that I will be able to produce at this point. Okay? I'm going to use up all my hydrochloric acid in producing hydrogen gas, which is kind of nice because that's what I want. I want hydrogen, so I really want to use up all my hydrochloric acid. Then I want to put enough zinc in there to get all the hydrogen out of my hydrochloric acid. So once I put that in there, I can now go ahead and calculate, the product. So now I use the 4 point, go ahead and use that over here. Use that, so for 4.800 moles of HCl, and then convert that to moles of HCl to moles of H2, and the mole ratio is now going to be 2 here and 1 over there. So when I work that out, now of course one more thing, this will give me now moles of H2, but I'm not asking for that, I'm asking for the mass of H2. So I need to do one more now. After I compare moles of substance 1 to moles of substance 2, I now convert to a mass of substance 2. So the last step, of course, is now going to be moles of H2 to grams of H2. In this case, it would roughly be 2 grams. Alrighty. Let's go ahead and use a little bit more sig figure here. This is going to be roughly 2.0159 grams of H2. And when you put all that together, moles now goes away, you end up with 4.8. In this case now, because I'm reporting an answer, I'm going to go ahead and go back to my original 3 sig figs. So 4.84 grams of H2, produced. This is now what I calculated using my stoichiometric calculation. So this is now my theoretical yield. That's my theoretical yield right here. So I predict that I should be able to get 4.84 grams of H2 from this reaction. Of course, the reality is I don't quite get that much. I only get about 4.50 grams. So with that, I can now calculate my percent yield. So let's go ahead and do that up here. So the percent yield now takes advantage of those two numbers. So for number 2, percent yield now going to be equal to, this is now my actual yield. So 4.50 grams divided by my prediction. Theoretical yield is 4.84 grams. Multiply that by 100%. Okay, and if you work that out, you end up with 93.0% yield. Okay, so not too bad, pretty efficient. Okay, 93% yield basically. All right, so that kind of wraps up the use of molarity in terms of limiting reactants, figuring out what that looks like, as well as using the mole ratios for stoichiometric calculations. So hopefully with this, you'll be able to then complete all of your homework assignment. Okay? All right, so that wraps it up. Okay, thank you very much, and take care until we see each other again next time.